We're working in section 6.4, where we have hit the point where we're talking about proportions, and we're going to take a look at example 4 next. Example 4 talks about a map. On a city map, a rectangular park has a length of 4 inches. If the actual length and width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? Now, when we talked last time, we talked about how when we're working with proportions, there's always going to be two things we're comparing. And it's our goal when we first look at the problem to figure out what comparisons are being made. So what things are being compared in this problem? Length and width, that's one of them. What else? Inches and feet. Actual versus map length, yeah, which is the inches and feet. Good. So it doesn't matter how we set this up. We can make the decision. We can either do inches on top, feet on bottom, or inches on left, feet on right. That's basically our choices. It depends on how we're doing the comparison. So what do you want to do? All right, inches on top, feet on bottom. And if we do that, then that means that the comparison that's made across the equal sign is map versus real life. Make sense? Okay. No, I didn't say that right. Length versus width is the other one we had. Sorry. Length versus width. There we go. All right, so in inches, what is the length of my park? 4. In feet, what is the length of my park? 500. And you may be looking at that and thinking, well, which do I use, the 500 or the 300? It goes in order. So since they said length and then they said width, length is 500, width is 300. Also, just reasonably speaking, we generally say that length is the longer unit for a rectangle than the width. Not that that's a big deal, but that can be thought of in that way as well. All right, how about width? What's the width in inches?
That's what we're trying to find.
That is what we're trying to find. So that's the x inches. What is the width in feet? Good. And now we have a setup that we can solve, right? Got all the pieces in there with the comparisons made in the proper order. So let's take a look. We have our 2 cross multiplications. So what do I have for my next line of this solving process? Yes?
Does it matter that one unit's in feet, the other's in inches?
No, because the inches are on top on both sides and the feet are on bottom on both sides. Now, it matters that we get the inches both in the same location. Like, let's say, for instance, on the left I had inches over feet, and on the right I had feet over inches. That would not work. So we're putting the inches and the feet in there only to make sure that we've got them in the right place. Yeah. All right, so what happens when I do the cross multiplication now? What do I get? So 500x equals what? 1200. Perfect. And you notice as I solve this, I'm leaving off the units because they aren't necessary. The units on the end are going to be in inches because that's what I'm finding is x. Okay. Then I can divide by 500. What is x?
12 over 5.
12 over 5. So think about it, though, in terms of the context of this problem. Would I leave it as 12 over 5? No, because it doesn't make sense when we talk about measurements. When we talk about measurements, we're going to change things into decimals. So what is 12 over 5 as a decimal? 2.4? Good. And it is in inches. So we make sure we write inches as part of our answer.
In this case, if we started with, like, since we're doing fractions, would it be okay to not leave it in a decimal like here?
On this one, it would not be okay to leave it in fractional form. And the reason why is because this is a practical problem, and you would not say that practically to a person afterwards. They would say 12 over 5 inches.
What if you change it to a
So-
mixed number?
If you write it in as mixed number, that would be okay too. Yeah, you could say that, 2 2/5 inches. Yeah, that would be all right. You could talk about it like that. That would be fine. But it wouldn't be okay to leave it as an improper fraction. So, good question. All right, let's take a look at another one. This one's a very interesting one. Very practical. This kinds of stuff happens. Sheila and Dora, they're working on a project together, but they work a different number of hours. One of them works for 3.5 hours, and the other one works for 4.5 hours. But they get paid for the project when it's done, just a total amount. Now, I don't know about you, but If I'm Dora, I don't want to get paid half of what the amount is because I worked more than Sheila did. So we were going to try and find a way to make this appropriate so that they actually get paid for the amount of work they did in an appropriate way. Did you understand the sort of crux of the problem here? We want to get paid the amount we really worked. Okay? All right. So what are we comparing in this problem? What are the comparisons?
Money and hours.
Okay, so the money we make and the hours that we work, that's one comparison. What's the other one?
Sheila and Dora.
Sheila and Dora. Okay, so what do you want to do with Sheila and Dora? Do you want to do Sheila on top of Dora, or do you want to do Sheila on the left, Dora on the right?
On top.
All right, so you're going to do Sheila compared to Dora. All right, I'm going to show you how to do the setup with this comparison, which is the natural way to do the comparison, and then I'm going to show you another option that you probably didn't think of because nobody said it. Maybe you thought of it and you just didn't say it, but the math actually works out to be easier if you can think of it in that way, okay? So we're going to compare Sheila and Dora, and we're going to compare how much they work, that is their hours, compared to how much they get paid. So far, so good? All right, so we've got two fractions with the equals between them. So Sheila, how many hours did Sheila work? 3.5. And I'm going to write it as 3.5. You can write it as whatever you'd like for the moment. We're going to be working with it in a minute, and the 3.5 will be a little friendlier to work with. How about Dora? 4.5. Now, here's the problem with the way it's set up, and it's not really a problem. It just ends up feeling a little bit awkward. I don't know how much either one of them should get paid, right? So it's not like I can just put in a number in one place and let the other one be X. Agreed? But what I can do is this. I can say that, let's say Sheila, I'm just choosing her arbitrarily, gets paid, so these are in hours, like we said. Sheila gets paid X dollars. I'll put the dollar sign at the end just so it's clean. If Sheila gets paid X, and they get paid 176 total dollars, what does Dora get paid?
176 minus that.
Right. And the reason this feels a little awkward is because of that 176 minus X. There's nothing wrong with it. It just feels a little awkward. And it means that I've got X in two locations in my problem, which also makes the processing of solving it a little bit more complex. So let's solve it, and then I'll show you another option on how to think about it, where the thinking about it is a little bit different, but the solving of it is easier, okay? So we're going to cross multiply.
I have a question.
Yes.
How do you get the 176 minus X?
Okay. So let's say, for instance, let me use an amount. Let's say, for instance, that Sheila made $30. Well, if they make $176 total, how would you figure out how much Dora made?
Oh, okay.
Right.
Sorry, yeah.
So you just take the total amount minus whatever she had. We're just calling that X
Okay.
right now. Yeah. All right, so we can cross multiply. One of my diagonals is 4.5x. The other diagonal, I have 3.5 times 176 minus x. So, I've got to distribute, right? What is 3.5 times 176? 16?
616.
Like that?
Yes.
Okay, thank you. And then the other one would still be the negative 3.5x then, right? So a little bit of algebra. What do you do next?
I have 3.5.
So 4.5x plus 3.5x is 8x. And that's equal to 616, which we'll divide by 8. What is 616 over 8? 77. So we have to stop, though, at the end here now and ask ourselves what we found. What is 77?
The amount that
That's the
she-
amount, good, the amount Sheila made. Because let's go back to the question. How much did each earn? So that's what we have to answer. So Sheila earned $77. How about Dora? 99. We'd have to subtract, right? We'd have to do the 176 minus Sheila's amount, 77, to find that she made 99. Yes?
The question says
They are paid the same hourly
Oh, okay,
rate,
okay, that
but they're not paid the same amount of money.
Gotcha, that makes sense. Okay.
Good point, yes. We want to make sure we're understanding the language correctly. Okay, you ready to see another option on how to think about this? Yes.
Okay.
What is your thought? Tell me.
I just added 3.5 and 4.5 and got 8 and divided that by 76. And then that's 22. And then I multiplied 22 by 3.5, 4.5, not 77.
Okay, we are going to do exactly that. But the thing I didn't hear you talk about is how the proportions were set up at the beginning. So my guess is you didn't use proportions. Indirectly, you probably did. You didn't realize you were doing it.
Okay.
Yeah, the mathematics that you just described is exactly what we're going to do. Okay, so what we're seeing happen here was a comparison between Sheila and Dora. Agreed? Okay, what I want to compare, so I'm going to erase this and start a different process. I want to compare Sheila, and we could likewise use Dora, to the total, like the combined effort. Okay? And I'm still going to use a proportion, and I'm still comparing the amount they work and the amount they get paid. So Sheila, like we said, worked 3.5. The total amount they worked, which is the 8 you came up with, would be the 3.5 plus the 4.5. That's 8. So 8 hours total was what was worked. 3.5 hours was what Sheila worked of that amount. Or if you use Dora on top, it'd be 4.5. We still don't know how much Sheila got paid total, but we do know how much, we do know how much they got paid total together. Together they got 176. So setting this up is a little bit more complicated because it doesn't really look like in the problem that I should be comparing Sheila to a total amount. Sheila to Dora is a much more natural comparison. But this comparison, by making Sheila compared to the total, gives a nicer proportion to work with. Because I only have x in one place. So there's that 8x that is going to come about. And then I still have the 176 times 3.5, which we did that a minute ago and got 616, right? And then I can divide by 8. So I end up with the 77 it was. So I still find the same thing. Sheila makes 77. And then to find Dora, I still would subtract to get my 99. What do you think? It's a little easier in the end. It's just a little bit less awkward because I don't have the 176 minus x in the distribution. Okay? Either one works though, right? But remember, just like I was saying when you were doing yours, the starting of the process, no matter what it is that you're starting, has to start as a proportion. Okay? So we're going to set the proportion up first, and then we can do all the mathematics with the addition, subtraction, multiplication, division,
So on
whatever
a
after
test,
that.
if we did it, you have to have, you want us to have a.
Oh yeah, and it'll say, I'm not going to let you go, I wonder if she wants me to use a proportion. It'll say, use proportions, da, 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 da. So it will be very clear and obvious if I want you to do it that way. But I'll tell you, in all of section 6.4, that's what you're using. That's the title of the sections, ratios, proportions, proportional reasoning.
It's one of those steps that I do in my head.
Yes,
So,
but I want you to show it because the students that you're going to teach can't see inside your head.
yeah.
Sometimes I forget that too. So we want to remember to show those steps along the way because the students aren't going to be able to see it unless we actually show it to them. Okay? All right, another one. At Rattlesnake School, we've seen a Rattlesnake School problem before, I think. Or maybe I have in my other class, I can't remember now. At Rattlesnake School, the teacher-student ratio is 1 to 30. So for every one teacher, there's 30 students. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 20? So what is being compared in this problem? This is actually a two-step problem, but what are the same thing is being compared in both steps. What's being compared? Teachers to students. Yeah, and there's this ratio going on, right? We've got a ratio of the numbers of the teachers to the students. So I can write, and I'm going to write it over here like this, with the teachers on top and the students. The teachers on the left and the students on the right. Or you know what? Let me do teachers over students. Actually, that's just fine, since I'm already being given a ratio. Teachers compared to students. So I'm starting out with a ratio that says that this is 1 to 30. So this means 1 teacher to every 30 students. That's a ratio, it's not the actual number, right? I don't have 1 teacher and I don't have 30 students. In fact, there may not be a single class in the building that's exactly 1 to 30. But the overall ratio is. So what am I going to do next? I mean, I've got a proportion set up. What's my proportion? Right, x over 1,200. So I know the number of students that I have. What's this x going to be finding for me? Yeah, it tells me how many teachers I have today with this ratio, right? All right, so I can cross multiply. I can find out that 30x equals 1,200. So x is going to give me what? 440, right? Okay, not 440. Okay, I thought I heard somebody say 400. Maybe my ears were deceiving me. 40 teachers. So I currently have 40 teachers. This is what's currently going on. This is today. But it's not what I want. I want to have a ratio that's 1 to 20, right? So I can do this exact same process again with the 1 to 20 and figure out how many teachers I really want to have in my school. All right, so we'll cross multiply. I get 20x equals 1,200. What's x? 60 teachers. So this is what I want.
Do you even have to do the middle part?
Which middle part?
Like the 30x equals 1,200?
You mean in terms of solving it?
Yeah, like do you have to show that work? Or can you just
In general, yes, because you're not usually going to have a 1 on top, so it's not going to be quite so clean, like the number itself. So yeah, in general, you'll show it. On this particular one, it's fairly straightforward. You probably wouldn't have to show it to be able to calculate that, so if you didn't, it probably wouldn't be a huge deal. But you definitely have to show the original setup. Okay. So what's the question that's asked?
how many additional teachers?
Yeah, so do you know how many additional teachers? 20 more. So we want to make sure we answer the question asked. The question asked is not how many teachers am I going to have someday. It's how many more teachers do I need to hire. So I need to hire 20 teachers. Make sense? Excellent. All right, we've got a student working, and she's making an error. So figuring out students' errors is a very helpful thing to be able to do. Ari is working with measurements and writes the following proportion. 12 inches to 1 foot is equal to 5 feet to 60 inches. How would you help her?
Use the switch so that it's the same on the bottom as the top.
Okay, why, Hannah?
Because
Let me help you a little bit.
like they have to have the same.
Specifically, what do you want to switch? Let's be more specific.
The 5 feet should be on the bottom to match the 1 foot on the other side. And the
Okay.
60 inches should be on top.
So she can I say reverse or switch, something like that? Okay. Switch 5 feet and 60 inches. Why? Why is she switching them?
Because it doesn't have to be like the same measurement on each side in order to cross multiply.
Clarify what you mean by measurement.
The unit.
Unit's the word we want, okay. So we want the same unit to be represented in the numerator on both sides, right? If we're going to compare them. Yeah, that sounds good. All right, so she should switch this 5 feet and the 60 inches so that the inches are both in the numerator. And feet in the denominator. In order, or something like this, for the comparison, in order for the comparison to be made in the same direction. Right? On the left, I'm comparing inches to feet. And I'm still comparing inches and feet on the other side, but on the other side, I'm right now comparing feet to inches. I need the comparisons to be made in the same order in order for there to be a proportion between them. Everybody good with that? It is worth noting right now that at least she has the numbers correct. I mean, it is true that 12 feet or 12 inches to 1 foot is the same thing that's being compared on the other side with the 60 inches and the 5 feet. So that part she got right. That's good. All right, here's another fun one. I like this question. We'll see this kind of a topic come back into play in, I think it's chapter 9. Example 8. Amy's friend told her that the ratio of boys to girls in her first grade class is 5 to 6. Amy was very surprised that her class would have only 11 students. What would you tell her? Okay, so what could it be then instead of 11 students? Don't think 30 will work. 36 won't either, but you're getting close.
35.
Nope.
30.
Nope. 22 is possible. 33 is possible. Okay, so why are 22, 33, 11, 44 all going to work, whereas 30 and 35 and 36, some of the other numbers we mentioned not? What's going on here?
They're not factors, they're like multiples of 11.
Okay, so where is Amy getting 11 from? Let's start there. She's adding the 5 and the 6. So right now we're comparing 5 boys to 6 girls. So it's probably worth noting just out loud to say she could really have 11 students. Is that possible? Yeah, it's definitely possible. It'd be a very small class, but that's a possibility. Tell you what, my daughter's class this semester, this year, she only has 6 students in her class, which is insane. It's a private school, so that's why. But my son has 13, so that's possible. If you were working in a public school, maybe she's got a special ed class. 11 would actually be quite large for that class, right? So 11's not completely absurd to think that she could have 11 students. So let's just kind of throw that out there first. But it wouldn't have to be 11 students, which is kind of where this question's leading to, right? So she's getting the 11 because she's adding 5 boys and 6 girls together, right? But this is just a ratio, which means I could have 5 boys and 6 girls, or what else could I have? 10 boys and 12 girls. So this would be giving me, we're going to write a sentence out or two in a minute here. This would be giving me 11 students on the left if I really had 5 boys, 6 girls. In the middle, I would be getting how many students? 22 students. What else could I have besides 10 boys and 12 girls?
15 and 18.
I could have 15 boys and 18 girls. So how are you getting 15 and 18, Allie?
5 times 3 and 6 times 3.
Right, the first 5 and the first 6 being multiplied by 3 instead of by 2, which would give me how many students?
33.
33 students. Now just for fun, we'll talk it through, but we won't write it down. If we multiplied the first 5 over 6 by 4 and 4, you would get
44.
20 students and 24 students, so 44 students total. 20 boys, 24 girls, so 44 total. All right, so and we could keep this process going indefinitely, especially if you were talking about a very large class. Maybe it's not, a small school. Maybe you were talking about something like the University of Oklahoma, where you have 500 students in the class or something like that. I mean, we could continue this process at a higher value if we needed to. All right, so the point, though, is that you see that we have lots of possibilities here, right? It doesn't have to be 11 students. So what are you going to tell her to help her to understand this?
It's a simplified version.
Okay, so the 5 to 6 is a ratio of boys to girls that may, or you could say could or would or should, or I don't care what you use, but it may have been simplified from the actual number of boys compared to girls. And it would be wise for you to give an example that matches one of the ones you've talked about and say something like, for example, 10 boys and 12 girls is a ratio, I'm going to run out of space, ratio of 10 to 12, which simplifies to 5 to 6 as well, but would give me 22 students, not just 12. I'm sorry, not just 11. Start with 11. Does that make sense? All right, everybody good? All right.